So you can start, please, Martin.
Okay, so as I was saying, we found these 4 equilibrium points for our system of nonlinear equations. And what we learned in the last lesson is that when we have a system of nonlinear differential equations, so we linearize it to apply the rules that we learned for the linearized system, where we compute that A matrix and then compute the eigenvalues and eigenvectors to conclude if the point is stable or not, if you have a saddle point, etc. So what we did in the last lecture after computing this was to conclude that this point A, the matrix A for this point, was the identity matrix, so 1, 0, 0, 1, and the eigenvalues were 1, 1, so it is unstable. So the solution goes away from that point. And then based on the signal sign of the derivatives, we concluded that here the solution goes to C.
Can you use a different color?
Yeah, sure. If we
Say
start
red
here,
or something like that.
in the x1 axis, we go to C here as well. And
all those points are aligned. So all the horizontal axis is part of an orbit, and the same from the other side.
And then, for B, we also concluded that the solution goes to B if it starts in the x2 axis.
You can use the same color because it's just to show the trajectories.
Okay. Something like this. I'm sorry, it's really difficult to draw here. And then Professor asked us to compute the A matrix for point D and point C and compute the eigenvalues and eigenvectors when necessary. So, which one did you pick, or did you do for both of them?
I tried to calculate the C value.
So do you want me to do the D?
For me,
Okay.
yes.
So for point D, the A matrix which I obtained was minus 2, 2. Then I computed the eigenvalues. So the determinant of A minus lambda I equal to 0. And this gave me the values of lambda 1 equal to -1, and lambda 2 and since these values of the eigenvalues have a real part that is negative, we can conclude that point D is stable. So the solution goes to that point.
Locally, what is the shape of the trajectories? Locally.
So locally,
there was one trajectory that we could find exactly that connects A and D, remember?
Oh yeah, we concluded that the system of equations is symmetric. So, and then we computed when x1 is equal to x2. So if we start in that
maybe
line,
you can draw the line between A and D.
yes.
And then after D also.
Sorry, wait. Okay, so we had this line, x1 equals to x2.
Okay.
And it goes to D if we start this line. So in this case, I also computed the eigenvectors, although it wasn't necessary in this case, right?
Yes, it's in this case it tells you very little, so it's immaterial. What is the shape? I mean, in general, what happens close to D?
So all the vectors go to D.
Goes to D. So you have a number of vectors that probably turn a little bit because they are exponentials. They are not always straight lines. You can put a number of vectors close, not so big, a number of lines there. Can you place that? Okay, well, that's okay, but placing the diagram, not okay, in the same diagram. Let's try to see if we can come to the conclusion of what is the type of solution that we get. Good. Okay, now, and that's it. Now, Cave.
Okay. I'll try my shot, okay.
Maybe we can clear the lower part of the whiteboard.
Okay.
I'm not seeing anything. Okay.
Now you see?
Yes. A white one, but it would be nice if we could write over the same diagram. The same diagram.
Okay. So you mean the...
Do I need to save it and...
Probably.
Okay, wait, then.
That's collaborative work.
I don't know how it works. Just a second. Okay, I can save it.
Okay. And
But
maybe Cave can write, you have to probably clean. There are no problems before we clean it. There are no questions to Emaxi or any issue to clarify?
No, I think.
So Jose, what she did was she picked up the linearization around point A, which is that matrix, computed the eigenvalues, and then the state trajectories are exponentials of these eigenvalues. So the eigenvalues are both negative. So you want having trajectories that approach point D locally.
Okay.
Okay. So can we cancel this? Any question? Jose went to the third dimension. No, to the fifth dimension. No, we are in the second dimension. So when he goes to the third dimension, let's see.
Okay, so so what should I do right now?
I saved it as
Maybe Maxi can cancel, apart from the diagram, cancel
okay.
Yeah, clear the
matrix
calculation. Yeah.
so that Cave has place to write.
Let me
Okay,
just
and now Cave, are you able to write on this?
Let me
I don't think so. Because
let me
Okay, so let's do this. Cave, use a piece of paper and copy the sketch and then do it, redo it before you present your.
I can send it to you, but I don't know if you'll be able to paste that.
I think it's possible to.
So you can see right now?
Yes.
Yes.
Okay.
Okay.
One.
So let me erase it. It's not very nice. Okay. So okay. I don't know. Sorry. Okay. Save it. I'm trying to use the Emacsys file.
But it's an image, so I don't know if you can
Okay.
open
So
there.
I think I cannot open it. Yeah.
I couldn't save it. There's another.
Okay. So now I'm going to. So yeah, this is the.
No, so I'm sorry, I was offline. I am having a lot of troubles with the internet.
You lost nothing because we're still.
Yeah, struggling with the
Okay, we know that is x1 and the other is x2.
So here is the. I put like C here. Sorry for my writing. So I got this point, which is C. So the matrix I got was this one actually. So if the A is equal to -1, minus 0, and so I wanted to calculate the eigenvalue like this. So So actually I got the point, so I'm writing here for the lambda 1 I got actually -1, and lambda 2 I got 0.5 or
No, okay, good.
so, which means also trajectory will go like this.
I'm not so sure.
Ah,
Well, that is true, but it's not a. When you have one eigenvalue positive and one negative, what do you have to compute?
I got to like eigenvectors.
Eigenvectors. So the eigenvectors is what define the directions in which you approach or you go away. You have to compute the eigenvectors.
Okay, so the eigenvectors I calculated. So I don't know. So should I erase it?
Yes, you can write.
Okay.
But don't cancel the eigenvalues because it's don't cancel that. I would okay.
I will write it again. So I will write it so on a corner. So I will again. So I don't know. I didn't write it very well in this whiteboard. So because it was my first time, but
You have to switch the rubber to the pencil.
switch. Sorry, I don't know how to. It doesn't work actually. I don't know.
Because you are not selecting the pencil. On the top, you find menu.
Draw.
Draw.
Yes, draw. And then like the wavy shape.
Ah, okay. So thank you.
Right.
So the eigenvector, as I mentioned, it was like this. The lambda 1, I got like -1, and lambda 2 was like 0.5. So I had to calculate the eigenvectors. So in this case, so I calculated and I got the point for the eigenvectors. So like this.
So don't write there because there is where you are going to place your diagram. Write
Okay.
a little more to the right. Okay, that is okay, but
Okay.
Whoa,
Is it okay? So
don't leave it there.
okay.
That okay, right from there. So
okay.
the V1 is what?
V1 I got for like 0, 1, 0.
So that's V1. V1
Yeah.
equals, right? V1 equal to, because it's important.
Yes.
It's not just to say that you have two eigenvectors, you have to associate them with the eigenvalues. So
And V2 I calculated, and it was minus and 1. So this is the eigenvectors. So which means associated the points actually here, which means the value will go.
so let's try to use a different color to mark the
Okay.
eigenvectors, the directions of the eigenvectors.
Okay. So which means actually
1 is 1, 0. What is 1, 0?
So the vector 1, 0, it means the x1 is like 1 is here, and the zeros.
No, but
like,
you are starting. I mean, now
yeah,
your origin is point C. Okay?
yeah, the original point
So it's
exactly.
from the origin you count 1,
Yeah,
1, and then one is not there. Along the x dimension, x1
Yeah,
dimension.
yeah.
Yes. Okay. You count one, and then you count 0. Okay, so
yeah.
But what are you drawing? What are those arrows?
So I mean, it will go toward to this way. You mean yes?
No, I don't know. What are those? What is the meaning of those arrows?
Which means if we move from here, so the origin, it will go toward to the like a 1, and the 0 is like the x. So yeah.
Cafe.
Yeah.
You are doing a linearized analysis. So you forget about the origin. The origin is away. You are considering what is going there. So start by marking the directions of the eigenvalue of the eigenvectors. Starting from C. So you have one eigenvector starting in C, which is 1, 0. So mark the vector 1, 0 from C. Cancel those arrows. Cancel those arrows that you have. Okay. Leave it there. So now use again something, some other color. Okay. Now mark the vector 1, 0 from C.
1, 0.
1, 0.
It's like we'll go to this way. Yes, am I right?
Yeah, the direction is immaterial. What is important is the direction. So just put a small line without the arrow. Not to confuse you.
Okay.
So and that cancel the arrow. And cancel the 1, 0. You know that's it's V1.
Okay. Right now we'll do it
Write
again.
some small stick in the direction defined by 1, 0.
Okay, here.
Okay, so good Lord, don't draw anything else. Stop.
Okay.
Now, V2.
V2, it is like a minus, minus 1 over 3 and 1.
1/3 Okay, so plot it.
Plot it, which is like here, minus, if the origin must be...
Yes, so you move something to the right or to the left?
So it will be to the left,
To the left, because it's minus.
Yeah, yes, it's
and
minus.
And then you have to put 1, and that if that is stop, and that if that is 1/3, what is now you move 1 in the vertical direction, up or down?
Yeah, okay. Sorry for
but
this.
I mean, that is okay, but
you mean this direction, yes?
Suppose that C is the origin. What is the point minus 1/3 1? That's a problem.
Yeah, here. I mean this one, which is like minus 1/3, 1 over third. So like assuming, so this point.
So, but do something more or less in proportion. You think that? So draw the vector V2. Where is V2?
V2 is like this one.
Which one?
So sorry, let me just do it again. I made mistakes here. So with the other color, I will do it. So the vector is like minus 1/3, so which is this direction. One is like, so which would be like this. If it would be like this, it would be like this.
You think so?
So it is like a minus. It would be like
so why do you say that that is minus 1/3 1? Show me. That means that the horizontal.
Yeah. The horizontal. You mean this way? Yes.
Should be 1/3 of the vertical.
Okay.
Is that correct? Now mark one vertical line there.
Okay.
Draw one vertical line. No, not there.
Here, yeah.
What are you trying to do? You are trying to plot. Sorry. Okay.
Okay, so
you are trying to plot a vector.
Okay.
So there you plot, and you have plot the vector. The vector has components minus 1/3.
Okay.
So what is your unit? In the vertical is 1.
Yeah, in the vertical is 1. Yes. It is like.
So plot 1. It's immaterial whether you plot exactly 1.
Okay.
you can plot something which is of any length, provided that the other one is 1/3 of it. That's the meaning of having.
Okay, yeah, okay.
Because what is important in the eigenvectors is the direction.
Oh, okay. So I assume this is the one, like the vertical one, so which is 1, I assume.
So you are moving up 1 and to the left 1/3. So move starting on C, move upwards something. Move some direction.
Yeah. So I got it now.
For God's sake, move up.
Yeah.
Good Lord, up. No, forget about it.
Okay, up.
No, up. So clean the others. Clean everything.
Okay.
Let's. Oh, you have cleaned too much.
Okay. Sorry. So here.
Okay. So you have a vertical line now.
Okay.
Your vector is not at 1 because it has minus 1/3.
Yes.
So after moving up 1, you go to the left 1/3. So 1/3 of that direction. So move now to the left about 1/3. 1/3 of that. Okay.
Yeah. So
okay. So where is the vector now?
The vector is like this one.
Okay. So plot it.
Okay. So I got it.
Okay.
Okay.
And actually, what is important is the direction.
The direction.
So plot this direction. Plot this direction. Now forget about the errors because the direction of the vector v2 is immaterial.
Okay, you mean this?
It's a vector. We know that a vector has a something that points in the theory, but it does not matter because what matters is what matters when you what matters when you move is the eigenvalue. So you have this direction. You have two directions. One direction in the vector in the direction of vector v2.
Yeah.
So plot this a straight line in this direction, a straight line, not a red.
Yeah.
No, that is. Why are you plotting that?
You said that a straight line. That's why I'm plotting that one.
A straight line. Well, why? Sorry.
So this is like.
Let's think a little bit. Let's think. Let's don't use the white color. Use the red color to plot the trajectories. We did not came up to that point. We are just plotting two vectors. So cancel the right, cancel the red, cancel everything. Just leave the blue.
Okay.
Just leave the blue.
Oh, sorry. Okay.
Now, let's mark pick up the green. Pick up the green and plot a line in the direction defined by 1, 0 at point C.
At point C, so
but close like to C. Don't start away. Start to the right or to the left. So it's centered there. The direction is also described. Is also the direction goes also. You know what is a direction? The direction is something that goes there and goes the other direction. That's a direction. Okay.
Yeah.
It's not a sense. It's a direction. So it also moves to the left. It also moves to the left.
Oh,
okay, but over the blue one. So that's the direction 1, 0. That's the direction. Good. Now plot the direction defined by minus 1/3 one.
So minus 1/3 one. Yeah. So this one is like this one. This way.
Which one is this way?
The one minus 1/3 one is like this.
I mean, 1, 0 is a vector. It's a vector, but
here. So assuming like this.
Listen to me. What is important is not that you mark 1, 0. It's the direction. It's the straight line that passes aligned with this vector.
Yeah. Okay, I got it.
Okay. Now. Okay. What is the direction? Aligned with V2.
So V2, as you mentioned, it is like minus 1/3 and 1. So
Yes, that's right. So
if as you mentioned, if this one like would be like 1.
no,
So
forget about those axes because you are thinking locally. So
Oh.
mark here when something which is
like this way, if I want.
I'm sorry. Let me finish, please.
So yeah.
Because otherwise we won't go anywhere.
I
Please release the.
Okay.
Otherwise we won't go anywhere. So we have can even use this. Okay. So I want to change my color. So that's one direction. That's another direction. Now we had one point here and another point here. And we had one vector, which is V1. V1 was 1,
0, 1, 0.
0. And lambda 1 was what?
Minus 1.
Minus 1. And then we have lambda 2 equals to
1 over 2.
1 over 2, and V2
is
minus 1/3.
Yeah, minus 1/3 over 1.
1.
Okay.
Okay. Now, 1, 0, 1, 0 is something like this. But
Okay.
what is important is this straight line. So
Okay.
is this straight line? Okay. This is the direction defined by the eigenvector. You see?
Okay.
Okay. When you have a vector like this, the direction defined by this vector is something that is aligned with it. Okay.
Yeah.
Okay.
Okay.
Now
Okay.
we have the other one. So minus 1/3, or if you want 1, and then to the left minus 1/3. So you have something like this. So this is your vector. But now what is important is the direction. So okay.
Okay, now I got it.
Is this so difficult? Now, let's think about the trajectories. Okay, so here, what are the points that you say you go to here or to there?
So
let's pick up, for instance, a point here. Where do I go at a point here?
So you will go toward the.
Where do I go? Up, down, to the left, to the right?
Right. You will go probably to the right. Yes.
Why? Why am I going to the right?
Because it is like minus, as you mentioned. So the
lambda is negative, and I'm aligned with the eigenvector. So I go there. Okay. What about here?
Here you will go away because it is positive.
So no. Why is it positive? It's the same eigenvector.
Okay. Sorry.
So the eigenvalue is negative. So I go. Yeah. Okay.
But it also makes sense that because if C is an equilibrium point, it means that trajectories should always be towards the equilibrium point, no?
Not always. Could be an unstable equilibrium point. We don't know that.
Oh, okay.
Okay. Now, if I'm here,
Okay.
where shall I go? I'm aligned with the other eigenvalue here. Where shall I go?
Done away. In this
Done
case.
away. Yeah. So
I'm going
again,
away because remember
It's positive.
yeah, it's positive.
that xt is a constant. And then we have 1, 0, exponential of -1 plus k2, -1/3, 1, exponential of, this is minus t, and this is plus t divided by 2. Okay? So
Okay.
if I'm aligned with this eigenvector, I will stay aligned with it because this constant will be 0. And the exponential is positive, so I go away. Okay, this negative part has no meaning, so I will have something like this. Okay, and we have came to the conclusion based on the sign of derivatives that actually all these points go to the left, and all these points go to the right, and all these points go to the left. And here it will be the same, and we have here then something which was another point, and we also know that okay, close to here, I'm approaching. So what happens if I'm here, say here? Am I going
Away, I think you will go away if
like this?
yes.
What are the opinions of the others?
No, you should go towards the
I'm
points.
approaching, I have two movements because I'm moving to the eigenvalue due to this component, but I'm also moving away, so it's not that. But it is, I do something like this.
Oh, okay.
Okay? If I'm here, I'm doing something like this. Okay? So probably what happens is that this is not always a straight line, but it will approach that. And for instance, if I start something that goes, I will probably do something like this. Okay?
So this means that C, so the point that Cave now calculated is an unstable equilibrium
It's
point.
an unstable, it's a saddle
And
point.
the D, so that
D is stable.
maxi is a stable, right?
D is stable, that's right.
Okay.
So you will probably have something like this. Okay? And this is symmetric, so if you compute the others, that will be something like this and like this. So this goes there, this goes there. Actually, over the axis, you stay at the axis, and you have an equilibrium point. And then if you do a similar analysis, you probably do something like this. Okay?
Okay.
Which means that if you approach, you are converging to this point because you want to cross this line. Okay, so this is more or less the diagram. Okay.
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 Let's see what happens let's see what happens when in reality. In reality, you get, this is a simulation. Okay, this is a simulation. This red line and this dotted line are not the directions of the eigenvalues. These directions correspond to the vanishing of the derivatives of x1 and x2. I don't know which is which, but these are not the eigenvectors. These are not the eigenvectors. Okay, so this is the simulation. So we were not far, no? We were approaching the this saddle point. This is a saddle point because it's unstable. No? If you,
I think we can't see the slides.
oh,
Okay.
I'm sorry. I'm sorry. That's a good point. That's really a good point. Now you can see it?
Yes.
Okay, so this red line and this dotted line, as I was saying, these are not the directions of the eigenvectors. Okay, these are the directions along which the derivatives of x1 and the derivative of x2, they vanish. When they vanish together, you have the equilibrium point. Okay? So in particular, this red line, what you think is where x1 vanishes or where x2 vanishes. Look at this point here. That's a subtle thing. What happens when the trajectory is the blue one, what happens to the trajectory at the red point when it passes by the red point?
It changes direction.
Change the direction and go back to the...
It's more or less in the vertical. No?
Yeah.
It changes direction, so it's a kind of maximum, an extrema. So it's vertical. If it is vertical, which derivative is zero, the x1 or x2?
X1.
X1.
X1 has a zero derivative. Okay, because you are in the vertical, so you are not changing locally. Then you start changing x1. So you know that all the trajectories will cross, when they cross the red line, they will do it in the vertical direction. Okay, and for the other one, it's all the trajectories will cross it in the horizontal direction because the derivative of x2 is zero. Okay, so that is something that one can also use, but we haven't used it. But anyway, by plotting the eigenvalues and the eigenvectors and using the information about the derivatives, we could reconstitute this. Okay. So Cave, you have to do basic exercises with a ruler and say what you have a vector. Now a vector, plot a vector. Okay, 5, 2, minus 5, 1, and so on. And
I didn't understand that. Yeah.
Okay. Okay, so I think that we should change subject.
And can I ask one thing?
Yes, yes, sure.
You know, can I ask something about this chapter of basic algebraic equations that you sent to us?
Yes.
Okay,
would you like to show what you are meaning, what you are referring to?
I'm seeing it in another computer. So I'm using now 2 computers.
Okay, but what is your question anyway?
Okay, so these linear combinations to determine determinants, So it's the PDF page 6. And it's the example 2.
Let me see where I have it. Let me see where I have it. So, okay, I have it here. Mhm. It's page. What do you mean by page?
6. It's the PDF page 6. So this one, yes, exactly.
Okay.
So the example 2. So it says that
Example 2.
exactly. So it gives us these 3 rules, A, B, and C, and then says that we should use these 3 rules to determine the determinant of the matrix. Yeah.
And what are the rules? If all multiplied by a constant, the value of the corresponding determinant is C times the original value. If you roll and interchange, the value of the corresponding new determinant is the negative. And if any multiple of one row is added to another row, element by element, the value of the determinant is unchanged.
Okay, so my question is in the first step. They say multiply the first row by 1.5, also by a half.
Using the both rules, the determinant of the matrix below is manipulated step by step. Okay, is doing what we call condensation.
Okay, but
Okay,
I just don't understand. It's this first. I don't understand this first step, because they say multiply the first row by 1/2, right?
Okay, so you have to, according to when you multiply by a constant C, the value of the corresponding new determinant is C times the original value. So you have to divide it. Okay,
Yeah.
so
Yes,
you multiply by 1/2, you have to multiply by 2, and that's the 2.
Oh, but why do we have to multiply by 2 here?
The idea
Which
is
was the
that
question?
you triangularize the equation, the matrix. Okay, so in the end, you end up with a matrix with a triangular form.
Yeah,
and
you
in
have
the
your
triangular
upper.
form,
You have your upper triangle.
computing the determinant is very easy. So it's -7 times 2 times 2 is the elements of the diagonal.
Yeah, that I understand. I didn't understand why we multiply by 2 and not by 1/2. So why is here 2? In the first step, why is determinant of A equals 2?
From A to the determinant of A, you multiply the matrix by 2, and now look at the rule. If all the elements in one row are multiplied by a constant, the value of the corresponding new determinant is C times the original value. So if you multiply by a constant, so if you want to keep the same determinant, you have to multiply by the inverse of that constant, and the inverse of 1/2 is 2.
But it doesn't say here the inverse.
Well, 2 is the inverse of 1/2. You agree?
Yeah, I agree. I just understand this why. Why is not? Because it says here, by the value of the corresponding new determinant is C. So, and if the constant is C, and
you want to suppose that you start this by saying determinant of A is this stuff, because this is A. So determinant of A is the determinant of A. Okay. Now, you are going to multiply the first row by 1/2.
Exactly.
If you still want to have the determinant of A, you have to multiply the determinant by the inverse of that constant.
Okay, so I understand. No, I completely understand what you mean. I don't know. I just, by reading the first rule, I don't understand that.
If all elements of one row are multiplied by a constant C, so by a constant 1/2, the value of the corresponding new determinant is C times the original value. So if you multiply the first row by 1/2,
Yeah.
then what happens? The matrix, this matrix, which is represented as a determinant, this matrix as a determinant which is 1/2 times the one of the original A. So you want to, if you want to have an expression for the determinant of A, you have multiplied by the inverse.
Okay, so that was the question. Thank you.
You understand? You understand the answer?
Yes,
No.
yes, I understand. No. I understand.
Let me have a new share.
I just thought. Okay, I understand the question.
So
it was just a matter of interpretation of the rule.
You start with a matrix A, and you compute the A is row 1, row 2. Okay.
Mm-hmm.
Now you multiply the row 1 by 1/2. Okay, so and you have determinant of A, it's determinant of R1 and R2. Now you multiply everything by 1/2. So you have another matrix which is not A, it's R1 and R2. Okay?
Okay.
And this is 2, this is 1/2 determinant of R1 and R2. Okay? Which is 1/2 determinant of A. Right? So when you do this operation, if you still want to have determinant of A, you have to multiply by 2. So the formula is R1 R2 is equal to what? If you write 1/2 R1 R2, this is not correct because there is this 1 2 1/2. So you have to multiply by 2.
Yeah. Okay. Now
When you have a C here, okay, you must have here a 1 divided by C.
Okay.
To have the same. That's how they built the example. Okay.
Okay. So thank you so much. Okay. Thank you.
Any other question?
No. Then it's correct. Okay.
Okay. So stop sharing. Now let me look at my slides for a moment.
So I calculated correct, but I had 1/2. So instead of 56, I had 40. But no, it's correct. Okay, very good.
You still have questions?
No. Now it's correct. So it's the same in the book.
Okay. Now let me look at what is in the chapter. Okay, I won't speak about oscillations. I will move to another thing. Okay, let's speak about stability. let's speak about stability. So this is file number 5, the direct method of Lyapunov. So we have an intuitive notion of stability. And we have already one method, which is perhaps not the most powerful method, because it does not always work, based on linearization. So if you want to study the stability of an equilibrium point, you linearize it, you compute the eigenvalues. If the real part of the eigenvalues is negative, then you have asymptotically stable point. But if your eigenvalues are pure imaginary, you can't say anything. Remember that? So if at least one eigenvalue is positive, then it's unstable. If all are negative real part, they are asymptotically stable. But if they are almost all with a negative real part, but there is a pair of complex conjugate, then you can't say anything, because these eigenvalues over the imaginary axis, they can tend, or they can fall down to the stability part or to the instability part. Okay, and also so this is a limitation, and let's see what happens with this other method. Okay, this is a very powerful method, the direct method of Lyapunov. So this is in Portuguese, but let's try to understand the mathematics. Okay, I say that I'm referring to the origin. So I assume that the origin is an equilibrium point. But what I'm going to say is valid for any equilibrium point. I mean, you can always shift your coordinates, and in the new coordinates are such that you are at the origin. Okay, then I say that the origin is stable in the sense of Lyapunov, using this definition that is like a game. So José gives me a number R, capital R number. And José wants the norm, that is to say, the size of the vector x, to be smaller for any t. So José wants the size of the state to be smaller than this capital R for any t. And I should be able to find a small r such that if you start at a point within this smaller ball, I will stay at the larger ball for all time. Okay, but this must be for any r. So this r, this capital R, can be as small as you want. So this means that I should be able to find always a small r, such that if my initial condition has a norm which is smaller than small r, then the state is smaller than capital R for all t. Okay, so this is a plot. You have this larger ball, which is the ball of radius capital R, and I should be able to find a smaller ball of radius small r, such that if the initial condition is inside this small ball, then the state will be inside the larger ball for all times, no matter how small the larger ball is. So Jose can squeeze the specifications, forcing me also to squeeze my initial conditions. Okay? You understand this concept? Portanto, quanto mais o José dá-me uma bola e quer que o Estado fique lá dentro, eu tenho que ser capaz de encontrar uma bola de condições iniciais que me garanta que eu fique lá dentro da bola do José. Okay? José gives me a ball, okay? And he wants that the state stays there, inside there. And I should be able to find another ball, which is smaller, of possible initial conditions, such that for all possible initial conditions, I will stay within the ball that José specified. Now, the difficulty is that this is not just for one ball, it's for all balls, no matter how small they are. Let me give you one example. Suppose that you have these equations. If you do a simulation, these equations, there is a periodic solution, you see. This axis is x1, and this other axis is x2. And you see that you have a periodic solution on this curve, on this funny curve. This corresponds to an oscillation, such that if you start in this boundary, you will stay there, always with the period, always repeating the states. If you start inside, you will approach it, but you never leave it. Okay, and 0, 0 is an equilibrium point or not? Can you tell me whether 0, 0 is an equilibrium point? What happens to the first derivative at 0, 0?
0.
0.
What about the derivative of x2?
0.
0, no? For x2 equal to 0, x1 equal to 0, this is 0. Not much difficult to see. So the origin is an equilibrium point, okay? And you know that if you do not start at the origin, you will stay bounded because you will never leave this encirclement. It's a so-called limit cycle. You will never go outside. Okay. Now my question is the origin a stable equilibrium point?
Yes, I think because it's 0, so
You say yes. Why?
so because
Remember the definition. You say it's stable if you find a ball. If you give me a ball, okay, in which
So,
you want the state to be contained,
yeah,
then I
so
should be able to find a set of initial conditions such that I'm contained there. But your ball should be as small as you want, okay? So you can divide it by the radius by 2 or by 4 or by 10 or whatever you want, okay? To make my life difficult. So, for instance, if I select a ball of radius, say this goes from -3 to 3 and -3 to 3. Suppose that I have a ball of size 3. Okay, can I find a set of initial conditions such that I'm always inside this large ball of size 3?
Yes.
Yes, because why yes?
We can start at any point that is inside that
Limit
shape.
cycle. It's a limit cycle, ciclo limite.
Okay.
Okay, it's a limit cycle. So any point inside the limit cycle, you don't go there, so you will never exist. Does this prove stability?
No,
Not because you have to. be able to find this set of initial conditions for any big ball. Can you give me an example of a big ball such that I'm not able to find a set of initial conditions such that I stay inside your big ball?
R equal to 1.
1. So it's a ball, what, something like this?
Yep.
Something like this?
Yes.
And then what is your argument?
So if we start inside that ball, it will
At
the
any
solution
point, you will go away because you
away,
are going to the limit cycle. Okay. So if you start, say, at this ball, no matter how small I select the ball of initial conditions, I will always go away from it. Okay. So this point is
Yes.
unstable. The solutions are bounded. They never grow. Usually we think stability means that you go to infinity. But no, stability means that if you don't start exactly at equilibrium, you will go away, not necessarily to infinity. You see, that's it has this subtle definition. Okay. Any question?
No.
No.
But sorry, the point inside this like shape, so it could be like the unstable or a stable, so but always a stable.
No,
I mean, in
I'm
the initial
thinking,
condition, yeah.
I'm thinking the initial condition is neither stable nor unstable. What is stable or unstable is the equilibrium point.
Oh, okay.
Okay. And the problem is that if you give me this ball and you say, find a set of initial conditions such that you stay inside this point, since all, apart from the ones that you start at equilibrium point, but you see that this R is bigger than 0. So it's not just one point, it's something around point, so some small circle. And I will always have trajectories that, or all the trajectories will go and approach the limit cycle. So I will always go away outside your large ball. You see?
Yes, I understood. Okay.
Okay, so this is the definition of stability according to Lyapunov. Now, another thing is that you say that a point is asymptotically stable if it is stable, as we have said before, and when time goes by, you return close to the equilibrium. Okay, so stability means that this finger is the equilibrium point, and I'm at equilibrium. Okay, I'm there. Now I disturb it a little bit. Stability means that I don't go too much away. Okay. Now, asymptotic stability means that I'm perturbed. I not only go too much away, but I will return to the equilibrium asymptotically, that is to say. When time goes to infinity, I will reach again the equilibrium. Okay, so asymptotic stability means stability and return to the equilibrium. Okay, that's the notion of asymptotic stability. In linear systems, if the eigenvalues are over the imaginary axis, you have stability, but not asymptotic stability, you have oscillations. If all the eigenvalues have negative real part, then the transient goes to 0, you go again to the equilibrium point, which is 0, 0. Okay? Now, this is Lyapunov. The poor guy shot himself with a shot in the head.
So this means that he found a point of instability.
Probably. He was unstable. He became widow suddenly, and I think it was after 1 week he shoot his brains. He gave a
Ru-
shot.
Is it Russian?
He was a Russian, yes. He studied in St. Petersburg, but he was a colleague of Markov. Have you heard of Markov, of the Markov
Markov.
processes? And so we studied there at the same time. He was a brilliant mathematician. Then this happened, this last part of his life happened in the, when he was in the Black Sea. He was for holidays in the Black Sea. His wife died, and after a week he suicided himself. And the motivation for his work was the stability of a rotating liquid, because the problem was something like the Earth or a fluid. The Earth is not a liquid, but it has a fluid. So what about the stability of the shape of the Earth? Okay, that's the. This was his PhD subject, his PhD problem. Okay. Okay. Now we have 8 minutes. Let me give you what is the criterion. The criterion is incredibly simple. And in the next lecture, I will speak about, we will try to explore it, okay? Now, we need a couple of notions. One notion is a positive definite function. So a positive definite function is a function of state. So imagine that at any point of the state, you have a real number. So at any point, at any coordinates of the state, you have a real number. That's a function of the state. Now, if at the origin of the state space, your function is 0, and if it is positive outside 0, then you say it's a positive definite function. Okay? It's something for a state in 2 dimensions, it's something like this. You can drink water from it. That's a positive notion of a positive function. Now, let me, we will go back in future classes to the slides, but the result of stability is very simple. It's this one. Suppose that you have a nonlinear systems, dx dt equal to f of x. No control, okay? No external variables. And you build a function, which is a positive function. You find a function, okay? You find a function. Next question you are going to make is, how can I find this function? Okay, there is no general method, only for certain problems. So somehow you find a function which is positive definite, and such that the derivative of the function with respect to time, when you travel along the trajectories, the solutions of dx dt equal to f of x, suppose that this is smaller or equal to 0. Then you say that the origin is stable. Okay? If this is smaller than 0, then it's asymptotically stable. So what is the interpretation? You have the state space and you have your function. The function is this cup here. Okay? Now you start with some initial condition, for instance, this point here, x0, and you integrate your state equation. So you have a trajectory. Okay? And for each point x of t, you can find v of x of t. Okay? So along this trajectory, which is an arbitrary trajectory, you can think that you start at any other point. So each time you follow some trajectory in x, and you see that you have the corresponding v of x of t. This is a sequence of numbers. Okay? if the derivative of v with respect to t is negative, what happens? Your sequence of numbers is decreasing. So you are approaching 0. That's why you are able to prove that if the derivative of v with respect to time is negative, along this trajectory, your system is stable. Okay. Now, how can I prove that for some v this is decreasing? You compute the derivative. You compute this derivative dv dt along those trajectories. We are going to do that next Wednesday. Okay, but the criterion is here. It's not a whole story. I have one book just with theorems about the Lyapunov stability. 160 pages, just the initiates of the theorems, not the proofs. So you can imagine there are hundreds of theorems about this study. But this is the basic one. Okay, this is the basic one, and allow you to study the stability. Okay.
Okay.
So the next time is to explore. We are going to explore these notions, and how to compute these derivatives and so on. Okay. So let's go away from the eigenvalues and eigenvectors. This is a kind of generalization of the concept of energy. In a mechanical system, if you dissipate energy, then the machine tends to stop, okay, at a stable equilibrium. And if V is a kind of generalized energy, and you are reducing the energy to 0, or to a minimum, better to say, not necessarily 0. Okay? Any question? Okay, so we stop here. Don't forget the first 2 homeworks. Try to do something and to send it to me, okay? So we see each other on Wednesday.
Yeah. So what about